All right, so inelastic and elastic collisions. So here we have the difference between the two, the difference and the similarity. So if a collision is inelastic, momentum's conserved, kinetic energy is not conserved. If a collision is elastic, momentum again is conserved, but kinetic energy is also conserved. So look, what's the similarity between inelastic and elastic? The similarity is that momentum is conserved. Momentum is conserved in all collisions, assuming the only force present is the force of the collision itself. So no friction, nobody's coming up and pushing on, there's no extra pushes or pulls besides the force of the collision itself. All right, so what's the difference between inelastic and elastic? So in an inelastic collision, kinetic energy is not conserved. In fact, a very common thing to find in a collision is that you lose about 98% of the initial kinetic energy. Like a bullet going into a block, you shoot a bullet into a block, you're going to lose like 98, 99% of the initial kinetic energy. If they tell you that the collision is elastic, what they're telling you is that kinetic energy is conserved, which simply means total kinetic initial equals total kinetic final. If the problem does not mention if it's elastic or inelastic, then which one is it going to be? Inelastic. If they don't say what it is, it's safe to assume that it's inelastic because most collisions are inelastic. Okay, so let's just look at this in a little more detail. So here we're looking at inelastic collisions. So in an inelastic collision, like I just said, momentum's conserved. Now notice I have two equations here for conservation of momentum. When would you use this first equation right here? This first equation is for when the objects do not stick together. And then this second equation is for when the objects do stick together. And I want you to recognize that these two equations are the same equation. It's just that in the second equation, if the objects stick together, then this velocity and that velocity are the same, and you can factor it out. Okay? Yo.
How do you know if they're going to stick together?
Oh, they'd have to tell you. The problem would have to specify that the objects stick together. And if it doesn't specify that, then you can assume that they do not stick together. Oh, and you know what? One thing I want to mention here. So look, so the second thing, the second characteristic for an inelastic collision, kinetic energy is not conserved, meaning you're going to lose a bunch of kinetic energy. Where does the energy go? Where does the kinetic energy go that's lost? If you look right here at this diagram, what happened to the back of the truck and the front of the car? It got deformed. That's where the kinetic energy went. Does it take energy to jack up the back of your car? Yeah. So loss of kinetic energy is due to deforming the object or objects. All right, elastic collisions. So again, momentum is conserved. Momentum is always conserved in a collision. And then we have a second thing conserved, which is kinetic energy. So conservation of kinetic energy would look like this. So this right here is kinetic 1 initial, kinetic 2 initial. So you add those together, and what you have is the total initial kinetic. So what we're saying here is the total starting kinetic energy before the collision is going to equal the total ending kinetic energy after the collision. Now, I want you to write something down. In an elastic collision, elastic collisions always have two unknowns. And the most common thing they're going to have you solve for is V1 final and V2 final. In other words, what's the velocity of each object after the collision? So just look at this example right here. So let's say, bless you, let's say this is M1 and then this is M2. So we have the initial velocities. These two carts come in, boom, they hit. If they told you that this collision was elastic, there would be two things you're solving for. Elastic collisions always have two unknowns. So guys, if you have two unknowns like this, how many equations must there be to solve it? Two. And here they are. You have conservation of momentum, and you have conservation of kinetic energy. Now, if I were a big meanie pants, I would just leave it like this and say, all right, guys, solve it. But if I did that, you would find yourself spending a lot of time on the algebra. What would make this very difficult to substitute this equation and this equation together? If you tried to do it, you would spend a lot of time. Who sees what would be insanely hard here? Let me go a little further. This is your unknown, so you're looking for V. You got V1 final, V2 final, and then down here, V1 final, V2 final. You're going to substitute these two equations together. What would be ridiculously hard here? The velocity is squared. If you look at this equation right there, the velocities are squared. The algebra would get really, 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 really crazy. So that brings me to this third equation. So everybody look at this third equation. Now, where did this third equation come from? This third equation came from combining the conservation of momentum equation and conservation of kinetic energy. It's basically this equation here and this equation here substituted together. I'm not going to show the derivation of it. Just take my word for it. But long story short, here's what I'm telling you. When you have an elastic problem, there's going to be two unknowns. You're going to use this equation and this equation. Forget about this equation, right? The conservation of kinetic energy equation, it's going to be too much because the velocities are squared. So you're going to combine these two together and solve for the two unknowns. All right, so let's try a problem. All right, so we have two carts that collide, and notice the problem is specifying that the collision is elastic. And let's call this guy M1, this guy's M2. So this is V1 initial, this is V2 initial. And what you're solving for, you're looking for V1 final after the collision and V2 final after the collision. So I'll give you guys 10 minutes and then we'll solve it. And that's our lecture on elastic collisions. Okay, so our problem here, we have two carts that collide elastically. So I'm going to make some room to solve this. They each have a velocity of 3 meters per second. Now, the key idea, and if you're going to make a mistake, it's probably this. To the right is plus, to the left is minus. So I'm going to call this cart here M1. This guy is M2. So this would be V1 initial, and it's positive. This would be V2 initial, and it's negative because it points to the left. To the right is plus, to the left is minus. Now, what we're looking for V2 final after the collision and V1 final after the collision. So let's start with this I was about to say conservation of kinetic energy. Look, this equation here, I mentioned it came from combining conservation of momentum with conservation of kinetic energy. It's a much more user-friendly equation. So solve this for V2 final. V2 final would be V1 initial minus V2 initial plus V1 final. So all I did is I took V1 final, moved it across the equal sign, the negative became plus, became positive. So we have V2 final. Now, V1 initial is 3, so that's 3 meter per second, minus, V2 initial is negative 3 meter per second. So minus a minus becomes a plus. So what we're left with is this. V2 final is going to be 6 plus V1 final. Okay, so we take this equation, plug it in up here. So now we're working with the conservation of momentum equation. We're just substituting two equations here. So I'm going to plug into the conservation of momentum equation. M1 is 4. You know what, guys? I'm going to leave units off because I'm not going to have room with the units on, so I apologize. So that's 4 kilograms. V1 initial is 3 meter per second. Okay, M2, I'm right here. M2 is 6 kilograms. V2 initial, don't forget the negative, it's -3, equals, okay, so now I'm here. M1 is 4. V1 final is what we're looking for. Plus M2 is 6. And then V2 final is 6 plus V1 final. So we're going to distribute this. So now we have 12 minus 18 equals 4 V1 final plus 36 plus 6 V1 final. I think you guys can do it from there. V1 final comes out as -4.2. That's the answer for final velocity of cart 1. Now that you have V1 final, come back to this equation right here. So V1 final is -4.2. So therefore, V2 final must be +1.8. Now look, there's a nice thing about this. You can check your work. How would you go about checking to make sure you did this correctly? Well,
Plug it back in.
you can plug it back in because look, here's what should be true. The total kinetic before the collision. So how would you find total kinetic before the collision? You would take the kinetic of this guy plus the kinetic of this guy, add them together, that's the total starting kinetic, which I think comes out as 45 joules. Then calculate the total final kinetic. So what's the kinetic of this guy? What's the kinetic of this guy after the collision? Add them together. If it's an elastic collision, what should be true? The total starting kinetic should equal the total ending kinetic. So you can check your work. Make sure you did it correctly.